before we explore discharges controlled by electric fields. We will now conclude by examining a discharge where the application of a magnetic field fundamentally enhances its efficiency and power, the magnetron discharge. This configuration masterfully combines crossed electric and magnetic fields to confine electrons, thereby dramatically increasing the ionization rate and enabling high-density plasma generation. The foundational element of a magnetron is its specific field geometry. We begin with a DC glow discharge-like setup, typically with a cylindrical cathode and a concentric anode. A strong static electric field, E, is established radially between the cathode and anode. The critical addition is a magnetic field, B, applied axially, parallel to the cathode surface. This creates a configuration where the electric and magnetic fields are perpendicular to one another, a crossed field arrangement. To understand the resulting electron dynamics, we must consider the Lorentz force acting on an electron. The electric field component accelerates electrons radially outward from the cathode toward the anode. However, the magnetic field component deflects the moving electrons. Since the magnetic force is always perpendicular to the electron's instantaneous velocity, it does no work on the electron. It does not change its kinetic energy, but it continuously alters its direction of motion. The combined effect of these crossed fields is a complex drift motion. An electron emitted from the cathode is accelerated radially by the E field, gaining kinetic energy. As its velocity increases, the component of the Lorentz force becomes significant, bending the electron's path. Instead of traveling directly to the anode, the electron begins to curve, eventually being turned back towards the cathode. The electron is not reflected by a potential barrier, but by this magnetic mirror effect. It thus becomes trapped in a closed-loop trajectory, known as a cycloidal drift, hovering just above the cathode surface. This magnetic confinement has two profound consequences. First, it drastically increases the effective path length an electron travels before it is lost to the anode. In a simple DC glow discharge, an electron makes a single direct transit. In a magnetron, an electron undergoes a long looping path, circling many times near the cathode. Second, because the electron is trapped in the high field region near the cathode, the region critical for ionization in a glow discharge, it has a vastly increased probability of undergoing ionizing collisions with neutral gas atoms throughout its extended lifetime. The result is a tremendous enhancement in ionization efficiency. A single electron can now generate thousands of electron-ion pairs along its convoluted path. This leads to the formation of a dense, bright plasma torus, often called the ionization zone or space charge sheath, encircling the cathode directly within the region of magnetic confinement. The positive ions, being much heavier, are virtually unaffected by the magnetic field. They are accelerated by the strong electric field directly into the cathode, resulting in intense, focused ion bombardment. This physical principle enables the magnetron to operate at much lower pressures, as low as 10 superscript 3 to 10 superscript 2 Pascal, than a conventional DC glow discharge, which would extinguish at such low densities due to an insufficient collision rate. Here, the magnetic field compensates for the low density by ensuring that each electron has a high probability of a collision. The most widespread technological application of this principle is in magnetron sputtering. In this thin film deposition process, the intense flux of positive ions bombarding the cathode, which serves as the target material, causes the ejection or sputtering of target atoms. These atoms then travel to a substrate, where they condense to form a high-quality, uniform coating. The magnetron configuration makes this process highly efficient, allowing for high deposition rates at low pressures, which is critical for producing pure, defect-free films for microelectronics, optical coatings, and wear-resistant surfaces. In the magnetron discharge, the magnetic field acts not as a primary ionizer, but as a powerful confining force, trapping electrons to maximize their utility. This elegant solution to the problem of generating dense, low-pressure plasmas is the cornerstone of the multi-billion-dollar sputtering industry and stands as a testament to the power of fundamental plasma physics in driving technological innovation.